All right, let's get started. So you have your exam on this past unit on Monday and Tuesday of next week. Unfortunately, I couldn't schedule it on Tuesday and Wednesday. It doesn't really make sense to have a review session on Tuesday at 3:30, considering that everybody would have at least had to have taken the exam or be taking the exam, because you can't possibly take it after class. So unfortunately, there's not going to be a review session for this particular unit. With regard to titrations, what I've done is I have posted an additional example video of each one of these titrations that we've discussed, including a weak-base strong acid titration, which I'm assuming everybody can do based on what we've discussed thus far. If you're struggling at all with it, though, there is an example video posted that works through that problem. Okay? We got one more topic to cover here, close out this unit, and that is what is called solubility products. All right, and the important thing to note about this, just like our acid-based reactions that we've been doing, or at least our weak acid, weak base, is that these are at their basis equilibrium problems. All right, so yet another type of reaction that we will be studying the equilibrium of. If we rewind back to last semester, you spent a lot of time discussing these precipitation reactions. That was when you had two ions that were soluble. So for example, barium and sulfate. And when these aqueous ions find one another in solution, they stick together and they form this solid barium sulfate product. Right? And you had these solubility tables that help to predict whether or not a solid product was formed, whether or not an ionic compound was soluble or insoluble. And so this is one of the ways in which we lie to you when you're starting out in chemistry, where we divide the world up in this very black and white sort of way. Something's either soluble or insoluble, right? Throw them in those two camps. This idea of being insoluble is a little bit of a lie. Every compound, including barium sulfate, will dissolve in solution to some extent. Not very much, but some little bit of barium sulfate will remain as barium ions and sulfate ions. If we looked at the equilibrium in this reaction, it would very much so favor the products, but there'd still be a little bit of reactant left over. Okay? And so this is a precipitation reaction. A solubility product reaction is quite simply looking at a precipitation reaction in the reverse direction. So my precipitation reaction would be barium and sulfate combining to make this solid. My solubility product reaction would be taking that solid barium sulfate and splitting it up into its two constituent ions, the barium ion and the sulfate ion. All right, and having this arrow here is really misleading because really this reaction strongly favors the reactants. But what we're going to be doing is looking at the equilibrium in this reaction, and we call this solubility product. So this is a KSP, this is the equilibrium here. Just like our Ka reactions and our Kb reactions, we have this class of reactions where we take a solid and break it up into its two constituent ions, its cation and its anion, and we have these values listed for these KSP constants. So I can find my barium sulfate here on my table here. It tells me that the equilibrium constant for that KSP reaction is 1.07 times 10 to the negative 10. So what would we say about this reaction? Favor the products or the reactants? 10 to the negative 10. The reactants. And does it strongly or weakly favor the reactants? strongly. So again, we call these insoluble compounds because it's not like very much barium or very much sulfate is formed. But nonetheless, even if there's a little bit, that can make a big deal. Lead compounds, for example, not very insoluble, right? Nonetheless, even a tiny amount of lead in a solution is very toxic to us. So there are some things that we're very concerned about, even the tiniest little bit of it that's produced. All right, so what we're going to do is we're going to use this KSP value here to figure out how much barium and how much sulfate is formed. Okay, so first of all, everybody's going to take a second. I gave you this chemical equation, this KSP reaction. You're going to take a second and give me my KSP expression, my equilibrium expression. All right, KSP, we remember what over what? Or rather, sorry, equilibrium constants. We remember what over what? Products over reactants. And what's going to not appear in my KSP expression here? That's solid. And by definition, this is how these KSP reactions are set up. You have a solid reactant breaking up into two aqueous products. So what we're going to see is that our expression is always independent of the amount of solid that we formed here. So this would just be the concentration of barium ions, times the concentration of sulfate ions. Boom. Okay. So we're just going to note our KSP expression, independent of the amount of our solid. All right, so let's ask if 10 grams of barium sulfate is added to water, what is the concentration of barium ions at equilibrium? And if this is an equilibrium problem, what are we going to do to solve it? Ice table. I know, don't get too excited. All right, and since this is going to be independent of the amount of solid, this 10 grams of barium here is a complete red herring, or 10 grams of barium sulfate. It's independent of the amount of solid that you have. It doesn't matter if you had 1 gram, 10 grams, 100 grams, you would get the same concentration of barium that would form. All right, so this is not going to matter. So I'm going to do my ice table just in terms of what appears in my KSP expression, my concentration of barium, and my concentration of sulfate. All right, so we're going to do this one together, and then I'm going to set you up to do one on your own here. How much barium ion do I have starting out here? None, right? I've just added that solid. Same thing here, no sulfate. My value for X here, well, I kind of gave that away. My change box, going to be X. And these are products, so we're going to increase by that unknown amount. So at equilibrium, I'll have X ions of barium and X ions of sulfate. I'm going to take this KSP expression. I'm going to plug in my equilibrium value for the concentration of barium. I'm going to plug in my equilibrium value for the concentration of sulfate. And I'm going to plug in that 1.07 times 10 to the negative 10. I should probably look it up again. 1.07 times 10 to the negative 10 for my KSP. X times X is X squared. So then we're going to solve for X by doing what to both sides? Taking the square root. And I get 1.03 times 10 to the negative 5. 1, 2, 3, 4, 5. Boom. And I guess I should have said beforehand, would we expect X to be a big number or a little number? Do I think I'm going to get a lot of barium for this reaction or a little bit of barium? A little bit. This reaction very strongly favors the reactants. But notice, it's not 0, right? That's the whole point here. Is yes, it's going to be a little bit of an amount, but sometimes that little bit of an amount makes a big deal. All right? So if I'm going to finish off this question and answer my concentration of barium ions is equal to, I should go back and check my ICE table. All right, cool. It's X. So 1.03 times 10 to the negative 5. And what would my units be? Molarity. Molar. All right. Let's do another one here. Yeah. Say it again. I don't know what you're saying. Let me see. Yeah, it was 1.07 times 10 to the negative 10. Yeah, you did 10 to the negative 11? 10 to the negative 10. Okay, so first of all, you're going to give me the KSP reaction, right? The chemical equation for lead to chloride. All right, finish off this chemical equation here. All right, KSP reaction, and we need our KSP expression. Notice a very similar format to how we were doing our weak acid, weak bases. We need our chemical equation, our equilibrium expression, then we solve it all with an ICE table. I guess I could ask. Let's say we're trying to find out how many, what is the concentration of chloride ions? Well, because you know the charge of chloride is -1 from the periodic table. So you'd have a periodic table in front of you, but based on where it lives on the periodic table, then you'd have to work backwards. I will jump to this constants page real quick, but let me just point out something, because this is going to be one thing that we got to remember when we went over our equilibriums. All right, when I break this up, it becomes lead to AQ. But then how many chloride ions am I going to get? 2 of them. And we've been dealing with a ton of reactions that were 1 to 1 to 1 for a long time. So we have to remember when we do our KSP expression and our ice table, where this little 2 here, where my coefficient is going to appear. Right? Our coefficient appears in both our equilibrium expression and in our ice table. All right, so I'm going to go to our constants page here. I'm going to go down to lead. We got lead 2 chloride, PbCl2, 1.17 times 10 to the -5 is our KSP value here. All right, so again, in my balanced chemical equation, we've been working with a lot of 1-to-1s. Now I have 2 chloride ions. So when I do my equilibrium expression, it's going to be the concentration of lead times the concentration of chloride squared, right? My coefficient appears as an exponent in my equilibrium expression. Likewise, my change box, for every 1 lead ion that's produced, I'm going to get 2 chloride ions. Remember, that coefficient appears in your change box as well. So again, we've been working with a lot of 1-to-1s. Remember, we got to incorporate that coefficient into our equations here. All right, so remember, I'm going to take my KSP expression. We're going to insert that value that we looked up, 1.17 times 10 to the -5. This is going to be equal to my concentration of lead at equilibrium X times my concentration of chloride at equilibrium 2x, and that 2x gets squared. So to be clear, real quick, let me just show you a big mistake. It is not 2x squared, right? You got to put everything in this box here, right here, meaning that the 2 and the x get hit by that exponent. All right, so be careful. Real easy mistake to make. The equilibrium concentration is 2x. You got to pick that up and put it right here, meaning it's going to get hit with that exponent. Everything in that box gets hit by that exponent. And if we were really feeling lazy, we could go to our solve feature on our calculator. But the math isn't too crazy here. All right, x times 2x squared. Well, that would be 4x squared. So we got 4x cubed. Whoops. So 1.17 times 10 to the negative 5 equals 4x cubed. That means x is equal to the cubed root of 1.17 times 10 to the negative 5 over 4. All right, so I get to the end here. My value for x, 0.0143, and I'm done? All right, let's be careful here. I asked you for the concentration of chloride. If I look here at my ice table, the concentration of chloride at equilibrium is not x, but 2x. Right, so my concentration of chloride is going to be my answer times 2, or 0.0286, and then throw some units on there to be good, molar. As zoomed out as I can get it. Okay, so we got our KSP reaction. We're going to take this solid, break it up into cation and anion. We're going to make our equilibrium expression, right? And we're going to remember that our coefficients become exponents in our equilibrium expression. We're going to set up our ice table. Our ice table is going to be independent of the amount of solid that we start with. Doesn't matter how much. So we just got our products here. We got no products to start out with. All right. For every one lead ion that I get 2 chloride ions according to my balanced chemical equation. And then when we get our equilibrium box, we're going to plug that in to our KSP expression. All right, solve for x. Again, you could use your solver or you could rearrange algebraically. Boom. For x cubed, and then we solve for x. Cool. So we have these solubility product reactions, taking these insoluble compounds and figuring out just how much will dissociate in that solution. All right, so here's my value here. Okay. All right, so now we can discuss, using this here, we're going to discuss what's called the common ion effect. All right. So previously, I had asked you if 10 grams of barium sulfate is added to water, what is the concentration of barium? I'm going to ask you something slightly different. If barium sulfate is added to a solution of 0.1 molar sulfate, what is the barium concentration at equilibrium? All right, we can take our 10 grams. It's still going to be independent. All right, but the difference is now I'm not adding this to water. I'm adding it to a solution that already contains sulfate. All right, the common ion here for barium sulfate. It's already got one of those two in there. All right, well, let's look at our equation here. This is our KSP reaction. We're going to do that same KSP expression. All right. Concentration of barium times concentration of sulfate. But now take a second and build me my ice table. All right, so what's going to be the difference in my ice table here between when I added barium sulfate to water versus when I add barium sulfate to a solution that already contains sulfate ions? It's not going to be in the change section. The initial section, right? Now I initially start out with 0 barium, but I already have 0.1 molar of that sulfate in there. My change section is still that I'm going to increase by some unknown amount, but now I'm going to get x and 0.1 plus x for my equilibrium value. All right, we looked this up before, 1.07 times 10 to the negative 10. So so just to be clear, KSP, concentration of barium, times the concentration of sulfate. And now I'm going to take my equilibrium box for barium, plug it in here. Equilibrium box for sulfate, plug it in here. And again, KSP we'd looked up, 1.07 times 10 to the negative 10 equals X times 0.1 minus X. All right. In this case, it wouldn't be too bad to have to solve, and you could definitely use your solver. But for these, what's up? Plus X, I'm sorry. Thank you. Making sure everybody's paying attention. This one, it wouldn't be too bad to solve. I mean, you'd have to use like a quadratic. It would be kind of a pain in the butt, don't get me wrong. We could always do it with our solver. The good news is here is that for these solubility products, because these KSP values are so teeny tiny small, similar to our Ka values, but they're even smaller. I mean, if you look at this table here, this was actually a relatively large one. We got 10 to the 39 here, right? I mean, 10 to the negative 39 here. So the KSP values tend to be incredibly teeny tiny numbers. So because of that, when we're talking about these KSP reactions, and it's really in the context of these common ions, we can use our small x approximation. All right, we're going to say small x approximation is always valid for KSP problems. Meaning that 0.1 plus x is basically just 0.1. All right, and now our algebra gets much easier here. 1.07 times 10 to the negative 10 equals 0.1 times x. I definitely believe in y'all. What's up?
If you look at the x, will it change anything? No, right?
Say it again?
If you add the x.
If you did the real value, you would see that it would have very little effect. So much so that it would be so many decimal places away, like 8 decimal places away. You could do your solve feature on your exam and you would 100% be able to find the right answer. Right? Either approach would work. It's just so small. You know, again, 0.1 plus 0.1 times 10 to the 9 is changing it 8 decimal places are, 8 positions away. All right, and this is, of course, our concentration of barium according to our ICE table when we put our units on it molar. All right, so let's just summarize here our common ion effect. We have barium sulfate in water. The concentration of barium was equal to, I don't remember, 1.03 times 10 to the negative 5. And then barium sulfate in 0.1 molar sulfate, our concentration of barium is 1.07 times 10 to the negative 9. All All right, so was barium sulfate more soluble in water or in this common ion solution? In water. So that is the common ion effect. These insoluble compounds are going to become even less soluble if there's some common ion already in solution. All right, so we're just going to summarize. These insoluble they become less soluble in solutions containing a common ion. What's up? Kind of, it's a little bit more like the idea that like, oh, if this thing's at equilibrium and all of a sudden I add a whole bunch more of this to it, it's got to reach equilibrium by going back the other direction. All right, so we're going to get even less of this reaction occurring because we already have a bunch of this in there. But it only works if it's a common ion, right? So if I had like sodium chloride in there, I would still get the same amount of barium. So it's got to be an ion that's common to both of these here. All right, let's practice this again real quick, just so we can go from scratch. All right, we're going to grab a new compound. Let's do, oh no, aluminum hydroxide, that's crazy tiny. We're going to do calcium fluoride here. All right, so we're going to talk about calcium fluoride. So let's just make note, 1.46 times 10 to the negative 10. Right, and I want to know what is the concentration of fluoride if calcium fluoride is added to a solution containing a concentration of calcium of 1.2 molar. All right, we got these same three steps: KSP reaction, KSP expression, and ice table. I think I'm totally using that word wrong. It's equation, but whatever. You know what I mean. The expression is technically one side of the equal sign, not both. But you got it. I guess you could use it. All right, and again, we looked it up. That KSP value is 1.46 times 10 to the negative 10. So see if you can't take this one home. right, so if you want to check up here, I got my KSP reaction here. Calcium fluoride decomposes into calcium and 2 fluoride. That 2 is going to have to appear as an exponent in my KSP equation here. All right, in my ice table, I'm going to start out with my 1.2 molar calcium, no fluoride. That 2 also appears in my change box here, because for every 1 calcium ion that's formed, I form 2 fluoride ions. Sum them all up. So now I'm going to plug that in. What was it? 1.46. I'm going to use that small x approximation. So 1.2 times 2x gives me 2.4x. Solving for x here. I get 6.08 times 10 to the negative 11 molar. What's up? Oh yeah. Holy hell. That mistake that I really warned y'all not to make, I just made. Batting 1,000 today. All right. 2x squared. KSP 1.25 times 4. 4.8x squared. X equals, what is that? 1, 2, 3, 4, 5, 6. Okay. And then am I done? No, not yet, because I asked for fluoride, and fluoride is not X, but 2X. Or 1.10 times 10 to the negative 5. Put some units on it, molar. Okay, so now what if I mix this up a little bit more? All right, I'm going to tell you an unknown compound has the formula XY2. At equilibrium, the concentration of Y is equal to 1.1 times 10 to the negative 3 molar. What is the KSP of our unknown? Now, this might seem like a very tricky, completely different problem, but it's really not. All I'm doing is giving you a completely different piece of information. You're still going to give me your KSP reaction. That KSP equation. And build me an ice table. don't know what this is, but I know how many of each of them there are. So when this is just going to dissociate, I'm going to get one of my x's and two of my y's. And if you're lazy, you can just leave it at that, but we can be good here. We said that y had a -1 charge, which means that x must have a +2 charge, but I'll tell you, it's not like that's going to factor in anywhere, right? So you just need to break it up into how many of each of those components you have. That tells you what your equilibrium expression should be. All right, filling this in here. We don't have any at first. Of course, our change box has this x in there. We know we're going to increase because these are our products. And what am I missing from that change box? That coefficient of 2. Oh, it is. But remember how we get this box here. We're going to have to use this box to solve. This box, you're right. If we did our ICIS table, the value here is that 1.1 times 10 to the -5, or times 10 to the -3. And we're going to use that information to solve for x, right? You always do your ICE table with your initial, your change box being a variable, and your equilibrium box being those first two rows summed up. And then the question is how to solve for x in that equilibrium row, right? So absolutely that 1.1 is what equals y here. And that's how I'm going to solve for my value of x. All right, if 2x is equal to 1.1 times 10 to the -3, right? 2x is my equilibrium value of my y ion, my y anion. So that's equal to 1.1 times 10 to the -3. That implies that x has to be 1.1 times 10 to the -3 divided by 2, or what is that, 4? 5.5 times 10 to the -4. It will be when I go back and use this expression here. I haven't plugged anything into this yet. But when I do plug it into that, I will absolutely have to make sure to square it. Right? So then using our ICIS logic here, we're going to plug in, this is my value for y at equilibrium. My value for x at equilibrium, my cation is just that, I guess, yeah. My cation is that 5.5 times 10 to the -4. To be clear, let me make this orange x and y to distinguish between my little x in this change box. All right. Now, given our KSP expression, everybody take a second, plug in those equilibrium values, and tell me what that KSP is going to be. right? So that 5.5, I plug 5.5 times 10 to the negative 4. I plug that in for my cation. That 1.1 times 10 to the negative 3, I plug that in for my anion, and I square it. And I get 6.6, let's round it to 2, 6.7 times 10 to the negative 10. All right, if you remember when we learned equilibrium problems, we played this same game. I could give you two pieces of information. I could either tell you what the value of one of your compounds is at equilibrium, that you could use to solve for x, or I could give you the equilibrium constant itself, and that you could use to solve for x, right? So it's the same game that we were playing before. We're just using a different piece of information to solve our ice table here. Now I know not what this KSP value is, but I know what the value of my anion is at equilibrium. So I know what this 2x is equal to. So we have a different strategy for solving our ice table for that value of x. All right, so if we just want to summarize here. Okay, if we're given our KSP, we plug in our variables to our KSP equation and solve for x. If we're given instead an equilibrium concentration, we use that equilibrium concentration to solve for x in one of our equilibrium boxes. Let's say in one of our ice table equilibrium boxes. All right, same approach. Get your equation. Get your get your chemical equation. Get your KSP equation. Get your ice table. You just got different pieces of information that you're going to use to solve that ice table. In the one, if you have the equilibrium constant, you got to plug everything into that equilibrium equation and solve for x. That's the big, ugly algebra way. If you're given one of the values of those boxes at equilibrium, then you're going to use that piece of information to solve for x. And then you're going to plug it back in to figure out what your KSP is. I could have also figured out, and I did actually, what my other ion concentration was. All right? We got questions about this. What's up?
Sorry, could you please explain why you didn't put the concentration in the initial box? Why?
Because this is the constant. Okay, so I wasn't adding this compound. Maybe this question could have been a little bit clearer. I didn't add this compound to a solution that already contained those ions. I put this compound in water, and then I figured out that it had that many ions, right? So this is all the ions that came from this compound. They weren't already in there, right? So that meant that I didn't have any originally. That's what I had at equilibrium.
Okay.
All right? So yeah, so it was before this was like I put XY into, or XY2 into water. It dissociated. I measured how many anions I had at equilibrium.
And that's what you got.
And that's what I got. So that's why I used it here for my equilibrium, right? This value is equal to my 2x. It's not the initial concentration that I had.
Okay. Thank you.
Any other questions? What's up?
I was just wondering, if not a factor, but did you go for hydrogen in the calculator? Because all the KSPs you're getting are different.
I'm making liberal use of parentheses. So for this, for example, what I typed in was 5.5 times 10 to the negative 4, and then I had to square this one here. So that means I had to go parentheses 1.1 times 10 to the negative 3, and then square that whole thing. Otherwise, I square the 10 to the negative 3 and not the 1.1. Any other questions? This was more of a wrench in the works than I thought here. Okay, we got one more thing to do. And if you loved that one, oh man, you're in luck. All right, so lastly, we got to talk about what's called selective precipitation here. All right, I have a solution, and it contains a concentration of chloride equal to 0.01 molar and a concentration of sulfate equal to 0.01 molar. So I got a mixture of two anions. Are these two going to bind with one another? Why not? They're both negative charge, right? So these two aren't going to bind with one another. They're floating around independently, having a good time. All right? And now I'm going to titrate in lead ions. Okay? Lead forms an insoluble compound with both chloride and sulfate. All right, but what I want to know is which compound will precipitate first. All right, lead sulfate, lead 2 sulfate, or lead 2 chloride. Now, this isn't something you have like a gut instinct for. All right, we can do this quantitatively by going and looking at the KSP values for each of these compounds. So we're going to go to our table here. We're going to find lead sulfate, lead 2 sulfate, and lead 2 chloride. All right, we had done lead 2 chloride before, so we got that one. And we got lead 2 sulfate here. All right, so let's make note of these values. Okay, in terms of my KSP values, lead sulfate had that 1.82 times 10 to the negative 5. And lead chloride 1.17, times 10 to the negative 8. And lead chloride 1.17 times 10 to the negative 5. All right, and remember these equilibrium values, they correspond to these reactions here, where we take our solid and it dissociates into our 2 ions. I'm doing a lazy man's equilibrium arrow, 2-headed arrow. All right, so who's got a guess? Let's take a poll here. Who thinks it's lead sulfate? Raise your hand. And who thinks it's lead chloride? Raise your hand. And who's got no clue? Okay, wonderful. So importantly, we're talking about a precipitation reaction, meaning that we're talking about this reaction in the reverse direction. So if we're looking at this reaction in the reverse direction, which reverse reaction is more favorable? The one with the smaller KSP or the one with the larger KSP? Which one of these favors the reactants more, smaller or larger? Smaller, right? So the smaller value means that it favors the reactant side or that solid more. All right, so in this case, my lead sulfate will precipitate first because this reaction favors that solid reactant even more. All right, so when I ask which compound precipitates first, I'm looking for the smallest KSP value. Okay? All right, great. So now, at what concentration of lead will sulfate precipitate? All right, and this may seem tricky, but algebraically, it's actually one of the easier ones than what we've done today. What do we know about the relationship between the concentration of sulfate and the concentration of lead? Well, we get that from our balanced chemical equation and our KSP expression. So everybody give me that KSP. KSP equals the concentration of lead times the concentration of sulfate. And you're like, dang it, we got to do a freaking ice table here. Well, hold on. Let's take a second and just take stock of what it is that we have in this equation here. Do we have a KSP value? Yeah, we got that from our constants page. Do we have the concentration of lead? No, that's what we're trying to solve. All right, bummer. But do we have the concentration of sulfate in this solution? Yeah, what's the concentration of sulfate? Okay, so we just have one missing variable here. We don't have to do any fancy math here. All we have to do is solve for that one missing variable, that concentration of lead. Right? So this is actually algebraically much easier than what we've been doing up until this point. I have my 1.82 times 10 to the negative 8. That equals this concentration of lead that I don't know. But I do know my concentration of sulfate, that's 0.1 molar. 0.01, I'm sorry. Can we solve for this missing variable here? Rearrange by just dividing both sides by that 0.01, getting that variable all by itself. Times by 100. So our concentration of lead is going to be equal to 1.82 times 10 to the negative 6 molar. All right, so then using that same logic, at what concentration of lead will the chloride precipitate? right, again, I know my KSP value, 1.17 times 10 to the negative 5. I don't know my concentration of lead ions. That's what I'm going to have to solve for. But I do know that my chloride ions have a concentration of 0.01. And according to my KSP formula here, I'm going to have to square it. So divide both sides by that 0.01 squared. And we get a concentration of lead equal to 0.117 molar. All right, same idea. We didn't have to do any ice tables. We didn't have to worry about any equilibrium, because when we looked at our formula here, we had this variable and this variable. We only had one missing variable, which means we can just plug in and solve for that missing variable, right? Isolate that guy all by itself. All right? Now real quick, because this is a tricky one here. We'll go quick. What is the concentration of sulfate when our chloride precipitates? All right, importantly, lead sulfate has started to precipitate way before the lead chloride, right? Which means sulfate's being pulled out of solution. My sulfate concentration is continuously going down before that chloride starts to precipitate out. All right? But again, this isn't too terribly bad here, because if I look at my equation, do I know my KSP for this equation? Yes, from my table. Do I know my concentration of lead when chloride starts to precipitate? Yeah. So now all I'm missing is this one here. All right, I know this because it was the answer to the previous question of what was the concentration of lead when chloride starts to precipitate. So again, just plugging into this KSP expression, rearranging it and solving. Okay, so for the sake of time, I'll go quick. 10 to the negative, what is it? All right, so I'm just going to take that KSP, divide it by 0.117, and I get what should be a very tiny number. .56 times 10 to the negative 7, question mark, 1, 2, 3. Cool. Molar. Okay, so selective precipitation here. We have a solution already containing 2 ions. We want to know when those ions are going to precipitate out. All right, we don't have to do any ice tables with selective precipitation. It's just using those KSP expressions of those 2 compounds. Figure out what concentration of lead when the first ion precipitates, what's the concentration of lead when the second ion precipitates, and what's the concentration of the first ion when the second ion starts to precipitate. All right, that's the name of the game there. Yeah.
So is this topic going to be on our exam?
Yeah, this is the last bit of this unit.
Okay, and then also, if you have last year exam, would you post it? Or?
No.
No?
I don't post my exams.
Okay.
They always remain secure.
Yeah, thank you.